Hi, and thank you for the introduction. So today I'll be talking about using silicon horn transducers to ultrasonically stimulate nerves, and we'll be doing this using low frequency ultrasound. So a little motivation behind our work. So the vagus nerve is cranial nerve 10. It's part of the parasympathetic control of the heart and digestive tract, and it's located on either side of the neck. And upon stimulation, it's been shown to help relieve symptoms of epilepsy, post-traumatic stress disorder, as well as headaches. And so our goal is to create a device that can help to treat a post-traumatic stress disorder. So why post-traumatic stress disorder? PTSD affects over 24 million individuals in the U.S. alone at certain points of their lives. But current methods are quite invasive. And so here to the right, you'll see a electrical device that's implanted and wrapped around the vagus nerve, and it provides stimulation to relieve the PTSD symptoms. But as you can imagine, it would be very invasive, and so our goal is to create minimally invasive or potentially even non-invasive ultrasound devices. So there's a body of work behind using ultrasound to stimulate nerves. And for example, there's in even salamanders, rats, frogs, and in mice as well. But most of this work has been done with much higher frequencies. And so we believe that we can create a low intensity ultrasound device with similar results. A little bit about the action potentials in general. One of the major ways that the body communicates. The blue chart, each one of those spikes are different action potentials, and if you were to zoom into one of them, it would look similar to this plot here at the bottom. So the nerve cord, so we're using the abdominal nerve cord in the crayfish, and it's comprised of a bunch of different axons. And these axons are basically like a cable that's surrounded with this lipid bilayer, and it has channels, and by which we believe that they can be opened by using ultrasound. And so the opening of these channels allow for an influx of sodium channels, which will depolarize the cell, allowing for action potentials to occur and propagate down the nerve. So as far as our setup, we're using a function generator to send a sine wave to our transducers, and we're using the oscilloscope to lock onto the resonance frequency of the transducer before every experiment. And we're using the neural amplifier to amplify our signals 1000x, and all of this being acquired using a NIDAC system and automated using a MATLAB script. So here to the bottom, to the right, you'll see that's the abdomen of a crayfish opened up to expose the nerve. And here you can see faintly is the nerve cord of the crayfish. Here to the right is the transducer that we're going to be using, and the recording electrode to the left there. So this is the shape of the transducer minus the holder, and so it's horn-shaped, and it has PZT placed on either sides of it that's adhesively bound to it. And when it's when it's activated at its resonance, which is around 105.6 kilohertz, the tip displacement is proportional to the driving voltage. And so during our experiments, we're using 2, 8, and 14 volts peak. So more about the experimental design, we're using, as I mentioned, 3 different voltages, but we're also stimulating for about half a second. And we're sampling at 500 kilohertz, and the threshold at which we're considering a spike or no spike is 0.03 volts. So the sound pressure levels were also measured, and at the 3 different voltages, you see that it's pretty linear with respect to the applied voltage. And so we're getting around 20 to 120 pascals of pressure and 0.01 to 1 watts per centimeter squares of intensity for the different voltages. And this image to the top left is the on the hydrophone that we're using to acquire this data. So we also measures the temperature of the tip of the transducer when we turned on the transducer at the 3 different voltages. And as you can see that at 2 volts it's very flat. It almost didn't increase at all. But at 8 and 14, you see a slight increase. The reason we did this measurement is because we're trying to also understand what is causing this increase in firing rates. And there is a theory that it may be the temperature, but there's 2 reasons we don't think that may be the case. One is because crayfish aren't really known to have temperature-sensitive channels, and 2, the temperature increase that we're getting is really low. It's just 1 to 2 degrees. And so this is the transducer here in saline. Yeah. So as I mentioned, we are basically at this point we're recording just passive firing, because even though we don't stimulate the nerves with ultrasound or anything, there is still some type of activity going on, and so that's our control. And then for as I mentioned, about half a second we're stimulating the nerve, and then we record post-stimulation as well. And so we're comparing the control to the during stimulation to see if we see an increase in firing during stimulation. So as far as results, this is an example at 2 volts. And so the top plot here is before stimulation, and this is during stimulation. And each one of those pink spikes are an individual action potential. And so we overlap them at their peak. And the black line is the spike triggered average. So the average of all these pink plots over time. And so you can see that the amplitude of the spike triggered average does indeed go up. And we also saw an increase in the number of spikes before, compared to before and after. So this chart shows the percent increase over 3 different experiments at the 3 different voltages, the 2, 8, and 14 volts. And the first 3 experiments, well, actually all the experiments, we did see an increase in the spiking, except for the one right here. Now in experiment 3, we saw a nice clean increase as you increase the driving voltage of the transducer. And we believe that to be because at that point, we were able to lock onto the resonance frequency, whereas the first 2 plots, it shifted. So not only did we see the increase in firing rates and amplitude, but we also saw a difference in the shape of the spike triggered average before and during. So again, the top is before and the bottom one is during stimulation. And you can see that through the different stages of the action potential, the slopes increase when compared to before and during. So they increased every time. So now how much did they increase? So they increase almost 100% every time when you compare the before and during stimulation at the 3 different voltages, as you can see in these that are bolded. And we believe that this might be able to shed some light on the maximum current possible for each action potential. So in summary, we microfabricated a silicon horn transducer, and we had a resonance frequency of 105.6 kilohertz. And we did this in the crayfish abdominal nerve cord. Unlike mammalian nerves, these are unmyelinated, so that's something that we plan to do in the future, is work with mammals. So the sound pressure levels were from 20 to 120 Pascal at the different voltages from 2 to 14 volts peak to peak, and the percent increase was as much as 10%, and that was at the 14 volts. And after the baseline, after stimulation, did go back down to normal. So we don't think that we're doing any damage to the nerve. And lastly, the active potential slopes increased on the order of 100% every time. So as far as future work, we plan to try and understand a little bit more about the mechanism behind what's happening here. And so we want to use polystyrene beads to understand if it's maybe potentially radiation ports that's increasing the firing rates, or maybe it could be potentially acoustic streaming. And so we'll use, again, these polystyrene beads to see if it's flow that's actually involved there. And we potentially will also use, try to understand if we're damaging the nerve in any type of way, maybe causing small holes to occur in the nerve. And as I mentioned previously, we're going to be moving on to mammalian studies in rats or mice. So with that, I would like to thank the Sloan Foundation, as well as the Natural Science Foundation and Cornell University.